So let me introduce our next speaker. It's Mr. Filippo Gerin from Italy. So he is with Maffei's Engineering, so a structural glazing expert, so an engineering expert. And his topic will be the nonlinear analysis of curved laminated glass structures. So please welcome Filippo. The stage is yours.
Thank you. Today I will present our new code for the numerical analysis of curved laminated glass structures. We built this code from scratch at Maffei's Engineering with a collaboration with the University of Parma. Laminated glass, we have stiff glass plates bonded to a polymeric interlayer, which is it has a much lower Young modulus, and the interlayer is viscoelastic, but we model it its behavior with a quasi-static simulation based on load duration and the temperature. The challenge in modeling laminates with stiff and soft mixed layers is that the shear strain of the interlayers causes this warping of between the elements, and so you cannot use homogenized plate theories for that case, especially if you have non-rectangular geometries or concentrated loads. If you can do it by fully 3D discretization, but it's computationally too expensive. And there are some software for laminated glass, but often are limited to flat geometries, or they have a strain measure which is not exact. And you can use general purpose software for finite elements, but its complex use requires many parameters to be put by hand, so it's they are too difficult. Our solid shed model, we taken it from our work of Tse of 2002, and our work from Garcia at the University of Calabria. This is a solid shell model. We use one element for each layer of for each layer of each material, and for each element we interpolate bottom and top nodal values. That is the displacement and the position. We use a strain measure which is geometrically exact, so we can handle curved geometries and large strains. And with respect to fully 3D models, the difference is that if you want to use that models, you have to increase the degrees of freedom because you incur in numerical lockings. And we alleviate these lockings without the need of more degrees of freedom. And we do it by doing some assumptions. I present you here. For example, we have with our elements, which is a trilinear element, we have these three strain, which is quadratic on the thickness direction, the in-plane strain. The transverse is linear, and the thickness is constant. And we can eliminate the quadratic part because it's very small, because the thickness is not. The laminated glass has low thicknesses with respect to other dimensions. For the transverse strain, we eliminate the linear part because to alleviate the shear locking that occurs in small thickness elements. shear lockings works as these linear elements cannot model pure bending that you can model, for example, with quadratic shape functions. And in pure bending, you don't have the shear. But if you use a linear shape function, you get this artificial shear stress. And so you evaluate with a reduced integration method the strain in the middle side of the element. And so when you evaluate it there, the linear part goes away. And that's the assumption. Then, if you see here, we have a constant thickness strain along the thickness, but the in-plane strain is linear. And by Poisson effect, this will produce a locking. And so we use an enforced plane stress to remove the Poisson dependence. And so we have the don't cause any more numerical lockings. We do pre-integration in thickness, so we can reduce the number of Gauss points needed for numerical quadrature. And the last one is to remediate to trapezoidal locking, which occurs when you model a curved geometry with a linear element, a bilinear element. And the problem is that with bilinear element, the strain in the thickness, the thickness is correctly modeled only in the borders, and in the middle it's wrong because it's shorter, and this causes a thickness strain that is artificial, and so we assuming natural strains, you interpolate the thickness strain from the borders to inside. The advantages of this model is that it's computationally efficient with a number of parameters that is still limited to fully 3D models. We have a simple strain expression that we can evaluate very efficiently with lower matrix multiplications. It's accurate because of the exact strain measure, and we demonstrate accuracy in large deformation and buckling, and it's easy to interface this model with other models. For example, with other full 3D models. For the geometry, we do the mesh in the 2D, then we embed into the surfaces, then we embed the mesh in 3D, where we can apply single curvature, double curvatures. Then we apply the package in the thickness direction. We applied it by extruding the mesh along the normals. And so we have these 3 elements for the thickness. For the mesh, because we usually need complex shapes with holes, with loaded areas, and we want a good quality mesh, we built our mesh solver from scratch. And the mesh is built by using a diffusion. We diffuse not a temperature, but the direction of the line on the boundaries of the surface. And with this diffusion, we can put all the points for the elements, which results in good quality quadrilateral elements. We put the solver in a web application where you can define the glass simply without the need of many too complex interaction. You can simply put the boundary conditions, also ports, point loads, self-weight, point loads, and this application runs entirely online. So if you have also a tablet or a smartphone, it can run. It runs in our servers, and it builds automatically load combination with the right shear modulus for the interlayers. You can see the results of the analysis and compare it with the most used standard, European and American. And all the results are there, are then written in a PDF file that you can download. And this web application is entirely free and will be soon available. And check our site for information for the exact date where we publish it. And along with the web application, we created also a Grasshopper plugin. So you can interface our FEM code with parametric programming. So you can import external meshes or external surfaces from any project. And we created these blocks of code to apply the same feature of the web application, but in Grasshopper. Also, this suite of plugins, it's free and will be soon published. And the solution actually is sent also to our servers. So it's a lightweight, very lightweight plugin because we do the core calculations. I make here some comparisons with commercial software. For example, here is a curved geometry with, for example, interlayer of 2 megapascal under a uniform load. Here is some comparisons. You see that we compare it with respect to Hexa8 brick element and Hexa20 brick element of strand. Our solution is exactly the same of Strauss. And you see here is here we have maximum displacement versus the mesh, the number of elements in the mesh, and the maximum principal stress. And here is the computing time. Our model, as I said, has less degrees of freedom than, for example, Hexa8, which is a linear brick element. And this is in logarithmic scale. And it's a bit faster than a commercial software. Here's, for example, a triple laminate on a two-side support laminated glass with a pseudo-concentrated load in the center of the glass plate in the top surface. And we see again how our software compares, and the results are very similar for maximum displacement versus load, principal stress versus load. And here is the displacement versus the mesh size. So it's displacement versus number of elements. And you see here that with Strauss Hexa20 elements, which is quadratic brick element, we cannot even do over a certain number of elements because it takes so much. But the results are actually good. As a last example, we made a comparison with the software SJMapla for the pendulum impact for the DNN standard, which is 2 tires that fall from 1 meter height and with a mass of 50 kilograms. Here is a dynamical simulation, so you have to take care of the loaded area of the tires on the glass surface. And this is done by an equivalent spring mass system. depending on the strain of the spring, you calculate the loaded area and apply it on the glass surface as an external load. And each of these two ellipses. And here's the result with respect to MEPLA. It's time versus maximum displacement, which is very similar, and also for time versus maximum principal stress. You see here 3 typical times, where the first one, time 0015, it's you see the 2 ellipses for the stress when the pendulum is impacting on the glass. Second time is at the peak of the stress. And the third time is when the pendulum detaches from the glass and the laminate freely oscillate. We also build a neural network code to just make some previews for the stress based on the load condition on the geometry. And the power here is that a finite element calculation took like minutes to be complete, but with a neural network approach, the results are nearly instantaneous. And they are enough accurate if you just want to see if, for example, based on a load, you are expecting to make some tries. I've done with my speaking. If you're interested, check the site apps.mafface.it, and here we publish the date for the date where we publish the software. Again, repeat it will be free, and so check this site. Thank you.